Hello, this is David, and welcome to another episode of Everything Economics. Today we're going to talk about the Cobb-Douglas Production Function. So I'll go over some background information and then we'll do some quick exercises. All right, this is going to be the overview for this brief lecture. It's first we'll talk about what is the production function. Secondly, we'll show you the Cobb-Douglas form, and we'll discuss some key properties. I've got a few graphical interpretations that you can view, and then some applications. How is it applied? And then, of course, we'll go over a couple of practice questions. All right, well, what is a production function? Well, this shows a relationship between inputs, which are factors of production, and output. And the general form is that Q, or quantity, is a function of labor and capital. So L is for labor, K is for capital. A lot of people ask, well, why is K for capital? I have no idea. My economist professor did not know, so I don't know either, so I'm not going to worry about it, but that's what it is. This helps us analyze efficiency and returns to scale. So if you think about it, when you're in a factory, if you want to produce any kind of product, and I'm just going to say a widget, if you're wanting to produce so many widgets, well, you're going to need so much labor and you're going to need so much capital to produce each of those widgets. And so this helps us to analyze, well, how much labor do we really need, and how much capital do we really need to produce so many widgets or so many products or units of products. All right, the production function, the general form is that quantity equals the total factor productivity times the labor input, and which is raised to the alpha, and then times capital, which is raised to beta. And so we have Q equals output, A is total factor productivity, L is labor input, K is capital input, and then the alpha and beta are output elasticities of labor and capital. Let me explain alpha and beta a little bit more. When you add alpha and beta, it equals 1, that means you have a constant returns to scale. So for example, let's say you have 5 employees and 5 computers, or 5 machines. If you add one additional employee and one additional machine, so that you have a total of 6 employees, 6 machines, then you are achieving constant returns to scales, whatever the output is. If on the next example, if alpha and beta is greater than 1, that means you are increasing returns to scale. That means if you add one additional employee and one additional machine, you may be able to produce more than just the one additional unit. If alpha and beta is less than 1, that means you have decreasing returns to scale. That means you're becoming less efficient. You add an extra employee, you add an extra machine, but your output is diminishing. It's growing less. So you're becoming less efficient in your resources. So that gives us a diminishing marginal returns for each factor. So this is a graphical representation, and I'm going to get my pen out so I can kind of point a few things out. Here we have labor, and we have capital, and then we have ultimately our output. So we have kind of a 3D surface, and so as we increase our labor and or increase our capital, then our output should go up. Now the question is, how much does it go up? Does it go up with an increasing returns to scale, Or does it go up just by constant returns to scale, or do we have decreasing returns to scale? So that's our increasing, constant, constant or decreasing. And let me just returns to scale. Obviously, if you could be more efficient, increasing returns to scale would be fantastic. Constant return to scale is not bad, but if you are decreasing returns to scale, that means you are becoming less efficient, and you may have to reduce the number of employees, reduce your labor, or reduce reduce machines or capital. All right, let's go to the next slide, which kind of gives us a little bit more information. Here we're talking about isoquants, and isoquants is simply a line of production. So it's similar to an indifference curve in consumer theory. You might have heard of this in a lecture where some people are indifferent to preferences. I'm not going to go into that today, but certainly I'll probably do another lecture on that in the future. These isoquants, or these lines here, shows the different input mixes producing the same output. So if you look here, like if you're on this line here at 30, that means you are maintaining an output of 30 units throughout this entire line. And you could be having like maybe a high amount of high amount of capital and only a little bit of labor. So for example, you could be at this point, or you can have a lot of labor and less capital and be at that point. And whatever point you are on the line, you are producing 30 units. Same way with this one here, you're producing 20 units. And then, of course, at this lowest line, you're producing 10 units. So as long as you are on this respective line, you're producing the same amount of units regardless of how much capital or labor. You might have more capital, less labor. You might have more labor, less capital. But if you are on this line, then you are producing the same number of units. And the reason that it's convex is due to diminishing marginal rate of technical substitution. That means, that means when you're substituting one input for another. So, for example, if you're substituting capital for labor, and you have a change in capital, and you're substituting with a change in labor, you may become less efficient and you have a diminishing marginal rate of substitution. So, for example, how do I put this? A machine may be able to produce, if we have like 20 machines and 5 employees running those machines, then we could produce 20 units. But if we go to the other extreme, if we have only 5 machines and we have 20 employees, then there is a substitution effect. And I'm not going to go into that so much in this lecture because that goes into another topic. But it's basically it's a rate of substitution between capital and labor. All right, let's go to the next slide. So here's a basic example. And suppose Q, or the quantity, equals 2 times L raised to the 0.5 times capital raised to 0.5. So if L, or labor, is 16, so we have 16 employees, and we have 25 machines, then we simply plug in those values. So the quantity is going to be 2 times 16 raised to the 0.5 times 25 raised to 0.5, and we have ultimately a quantity which is going to be 40. And this just shows the balanced contribution of labor and capital. It's okay if you don't understand it, because then we'll go over some examples that we can work out. Basically, the applications of the Cobb-Douglas, it helps us like with growth accounting and the solo model, which I'm not going to get into today. It helps us to estimate productivity. So, like I said, if you're running a factory or you're running any kind of operation, you need to estimate how many employees and how much machines or how many computers or how much capital that you need to achieve a certain amount of output or quantity. It helps us analyze factor shares of income. And of course, empirical studies, it's useful in studies for economics and business. You'll see a lot of research papers that use the Cobb-Douglas production function. And so it's a helpful tool to help us analyze businesses and their output. All right, so here's some practice questions. So again, like I said, if you didn't understand it, that's okay. We'll go over these questions. You can pause the video if you want and work these out yourself, or you just go along with me and I will work them out. So for question number 1, it says if Q equals 5L raised to 0.6 times capital raised to 0.4, what happens if both L and K are doubled? So we are going to go ahead and write this out. So we have Q, and it's going to be, let's see, 5, and we're doubling labor and capital. So we're simply going to insert a 2. It's going to be labor, and it's raised to 0.6. Okay. And we're going to multiply that by 2K, because we're doubling capital, and that is raised to the 4th. Now remember, these are the alpha and the beta, these exponents, and they have an effect on the labor and capital, so with respect to output. And let's see, let's go ahead and complete this. We can take the 2 out, and for the alpha and beta, we actually add the exponents. So if you recall from maybe your college algebra classes, you add the exponent. So we have an exponent of 0.6 and the exponent of 0.4. Excuse me, I rewrote this wrong. It's actually 0.4. And so if you just add them, they're actually 1. So that's going to simply be 2. And that's going to be our quantity. So ultimately, when we double labor and quantity, we're simply going to get twice the quantity, or 2 times quantity. And what does this mean? Well, this simply means that the constant returns to scale. Constants return to scale. So you double your capital, you double your labor, you get double your return. You don't get decreasing returns, you don't get increasing returns, you simply have constant returns to scale. All right, Let's go on to the second one. And it says for Q equals 3 L raised to the 0.3 and K times K raised to the 0.7. What is the returns to scale? So remember, returns to scale, it could be increasing, it could be constant, or it could be decreasing. All right, so let's go ahead and work this out. Well, we know that alpha plus beta equals 0.3 plus 0.7. So that equals 1. If you recall from the earlier slides, when alpha plus beta equals 1, it simply means constant returns to scale. So for each additional unit of labor and capital, you will have a constant returns to scale. You're not increasing your returns and you're not decreasing. All right, well, I hope this helped you in understanding a little bit more about the Cobb-Douglas production function. If you have questions, put them in the comments, and hope you have a good afternoon or good day. Thanks.